Today's lesson focuses on empirical and molecular formulas. If you have discovered a new compound that has never been before identified, chemists need to take some time and determine the types of elements that are present in that compound, and then they go through two sets of steps to come up with the actual formula. The first is the empirical formula. They determine that first, and then they come up with the true or molecular formula that we are most used to seeing with compounds. So what is an empirical formula? This is the newer part of this lesson that you wouldn't have heard of before. And this is when we take the chemical formula and we reduce it to the smallest whole number ratio or reduced form of the elements present in a compound. So for example, octane has a molecular formula or chemical formula of C8H18. How can we reduce those numbers or those ratio of elements to give us the smallest whole number ratio? And if we divide both 8 and 18 by a factor of 2, we come up with an empirical formula. So chemists always will start with the empirical formula first, and then they'll scale up and they'll come up with a molecular formula when they first identified a compound. So the molecular formula is the formula that we know. It's the formula that shows the actual number of atoms of each element in that particular compound. So here's another example of empirical versus molecular formulas. Here is the molecular formula of glucose that we know. And then we take that molecular formula and we reduce it to its lowest whole number ratios. So we can divide everything by a factor of 6, and then we can come up with the empirical formula of the elements in that compound. So we have to be aware that for some compounds, the empirical formula could actually be the same as the molecular formula. So sometimes there is no real reduction. The other thing that we need to be aware of is that the empirical formula might be the same for many different compounds. So here's an example of benzene, a C6H6. And here's another example of a different compound, totally different, acetylene gas at C2H2. If you reduced both of those down to their lowest whole number ratio, you get this empirical formula. So the empirical formula is just simply used to tell you the ratio of atoms, but the molecular formula gives us, again, those actual number of atoms. And this is one of the things, particularly with covalent compounds. This is why when we are doing nomenclature in covalent compounds, we never reduce the formula, because what you would be doing is reducing to the empirical formula, which could quite possibly be the same for different compounds. So there's a few steps in order to determine the empirical formula first. So if a chemist found an unknown compound, they would put it through an analysis and they could figure out the types of elements that are there and also the percentage composition of each element within that compound. Once you know the percent composition, you can convert that to a mass of each element and then calculate the number of moles of each of the elements in your compound. Once you know that, you then figure out which number of moles is the lowest, and then we divide that lowest amount into all of the other mole values for the elements. So we divide each amount by the smallest mole value, and then that is going to give us a factor which relate to the subscripts in our formula. So let's try this example and come up with an empirical formula for this compound. So they give us the percent composition of the elements present. And so what we need to do is we figure out this percent composition if we're required to. If they give it to us, we can then determine the mass of each element. So the first thing we're going to do is we're going to assume a 100-gram sample. And this is nice and easy because if we assume a 100-gram sample and we're dealing with percentage values, all of those percentage values just become gram values. So 27.37% of 100 grams is 27.37 grams. So then we can just set this up and we can say that the mass of sodium is 27.37 grams. The mass of hydrogen is 1.200 grams. The mass of carbon is 14.30 grams. And then lastly, the mass of oxygen is 57.14 grams. It's a 7 right there. Now, careful with the hydrogens and the oxygen. So we're used to dealing with diatomic elements, but you're not doing that here because remember, all of these elements are part of a chemical formula for a compound. So what we're trying to do is figure out the subscripts for each of these. So don't assume that your hydrogen is H2 or your oxygen is O2. We're not dealing with these elements on their own. They are part of a compound in this particular example. The next step for us to do is to determine the moles of everything. So step 2 here, we're going to figure out the moles of sodium, and we're going to take mass divided by the molar mass. So we'll take 27.37 grams, and we're going to divide by the molar mass of sodium, so 22.99 grams per mole. And I get a mole value here of 1.1905 moles. We'll do the same thing for hydrogen. We have to figure out the moles of hydrogen, and we're going to take mass divided by molar mass, 1.200 grams, and we're going to divide by the molar mass, which is 101 grams per mole, and then we get a mole value of 1.188 moles of hydrogen. Let's figure out the moles of carbon now. So again, mass over molar mass. Sub in your values, 14.30 grams of carbon divided by a molar mass of 12.01 grams per mole. And we get a mole value here of 1.1907. So notice I'm keeping, 4 decimal places roughly, 3 to 4 decimal places. And then lastly, let's do the moles of oxygen. So same process, mass over molar mass. Remember, oxygen is not a diatomic here. He's part of a compound. So we just need the true molar mass of oxygen. So 57.14 actual grams over a molar mass of 16 grams per mole. And we end up with 3.5713 moles of oxygen. Okay. So then what we do next is we figure out, well, who has the smallest amount of moles out of these elements? And everybody's kind of close here, like sodium and hydrogen and carbon are all pretty close. But I mean, this is why we carry decimal places. So this is my smallest amount right there. And the third step for us is to go through and divide that smallest amount into all of the other molar values. So let's calculate the moles for each element now. So what I'm going to do is I'm just going to write sodium and a colon, and I'm going to put sodium's actual mole value at 1.11905 mole, and then I'm going to divide it by that lowest mole amount, which happen to be hydrogens. And you see they're fairly close, but we're going to write down this factor. So we're going to get 1.002 for sodium. For hydrogen, this is easy. They both have the exact same values, so we still write this down, and we divide hydrogen's value by itself because it's the smallest amount. This is an even factor of 1. Let's do it for carbon as well. So for carbon, we had a mole value of 1.1907 mole, and then we divide by 1.188 because that's the smallest, and this works out to be 1.002. So again, we see very close to factors of 1. For oxygen, oxygen's moles were 3.5713 mole. And then we divide by that lowest amount, 1.188. And now we get a factor of 3.006. So the last step is now to take these numbers, these ratio numbers, and convert them to a chemical formula. And because all of these are fairly whole, straightforward whole numbers, we can leave them as that. If I had a value over here, maybe of like 1.5, something, I can't put that into a chemical formula. We've never seen 1.5 before. So then we have to do an extra little step, which we'll address in the next example. But right now, step 4 is to come up with my actual empirical formula. And this is where I would have sodium with a subscript of 1, okay, but we never put a 1 in, so we'll just take it out. Hydrogen with a subscript of 1, but we never put a 1 in, so we'll take it out. Carbon with, again, a subscript of 1, we're not going to put it in. And then oxygen with a subscript of 3. And there is your empirical formula for this particular compound. Let's do one more example together for this, calculating this empirical formula of a compound that contains iron and oxygen. So again, step 1 is to determine the mass of each element. So they already are giving us the masses, so that's kind of nice. And let's just go straight into, so step 1 would be masses, and they've told us, okay, so we know them. Step 2 will be to calculate the moles now of each element. So let's calculate the moles of iron, and we're going to take mass over molar mass, 69.88 grams, and we divide by a molar mass of 55.85 grams per mole. We get an answer of 1.251 moles. And then let's do the same thing for oxygen. So remember, oxygen is a diatomic element when he's on his own, but he's not on his own. He's in a compound with iron. So when we calculate the molar mass and the moles of this, we are just using the true molar mass of oxygen, which is 16 grams per mole. It's a 6. And I get a mole value of 1.8825 moles of oxygen. So now what we do in step 3 is we divide our mole values by the smallest amount. So for iron, we're going to take iron's mole value, 1.251 mole, and we're going to divide it by the lower of the two values. So it happens to be iron, so we're just going to divide it by itself, 251 mole, and we get a factor of 1. For oxygen, we're going to take its mole value, 1.8825 mole. We're going to divide by iron's value because it's smaller, 1.251 mole. And then we get a factor here of 1.5. So these should be the subscripts in our chemical formula, but we've never seen a subscript of a decimal in a chemical formula. So we don't want that. We want whole number ratios of atoms. So what we have to do is we have to take the whole thing and we multiply it by a factor to get to a whole number. And you start off low. So you would multiply everything by a factor of 1. Well, that's not going to do anything. So you move to 2. If I multiply everything here by a factor of 2, then I go into a 2 for iron and a 3 for oxygen. And that works. Sometimes that won't. Sometimes you have to keep going and multiply by a factor of 3 or 4 to get a whole number ratio. So this here, the factor of 2 is good enough. And then lastly, we're going to come up with this empirical formula. So Fe has a subscript of 2 and oxygen has a subscript of 3. So what to do if you actually are asked to come up with the true molecular or chemical formula? Well, what you need to know is the empirical formula first. You cannot do this step without knowing the empirical formula, because you have to obtain the molar masses of the molecular and the empirical, and you just simply will divide them out and come up with a factor. Remember that the empirical formula is the lowest whole number ratio. And so it's a pretty easy, quick step to do. So it says a compound with the empirical formula CH was analyzed using a mass spectrometer. Okay, and this is where the mass spectrometer will tell us the elements present and then the weight of each of those elements compared to themselves. It determined that the actual molar mass of the compound was 78 grams per mole. So determine its molecular formula. So we know the empirical formula. So what we want to do is we want to calculate the molar mass of my empirical formula. So here I just have one carbon at 1201 and one hydrogen at 101. So I have a molar mass here of 13.02 grams per mole. And then what I do in the second step is I figure out a factor here. So I take the molar mass of the actual compound and I divide it by the empirical formula's molar mass. And then I will come up with a factor that I'm going to apply to the empirical formula and come up with the actual chemical formula. So this becomes 5.99, and we're going to round that to 6. And so then what we do is we take that empirical formula of CH and we multiply everything by 6, and we come up with a chemical formula of C6H6. So calculating the molecular formula is very easy. It's very simple. All the work is done in the empirical, and if you follow the steps that I gave you, you will not go wrong.